Welcome to A-level trigonometry. We're going to kick off by thinking about what you already know from GCSE maths. There will be a fair bit of trigonometry that you've already seen. You'll think in terms of right-angled trigonometry and non-right-angled trigonometry at this point probably. So use these diagrams as a starting point and write down any rules or formulae that you already remember. Pause the video, jot down what you can, and then unpause and compare. So this is what we have for a right-angled triangle. There are three main results, and these are known as the trigonometric ratios. Sine theta is just a way of describing the ratio between the side opposite the angle and the side known as the hypotenuse, which is always opposite the right angle. Cosine of theta, or cos theta for short, is the ratio of the adjacent side compared to the hypotenuse. And because in both of those cases we're dividing one of the shorter legs of the right-angled triangle by the longest side, we will always get an answer that is smaller than 1. For tan theta, however, we're dividing the opposite side by the adjacent side. Tan theta is the ratio of the opposite to the adjacent. You've come across this idea already in terms of the gradient of a line. So you can think of tan theta as being the gradient of the hypotenuse. And this one is not limited by a maximum value of 1 because the opposite side could well be greater than the adjacent side. In fact, whenever the angle is greater than 45 degrees, tan theta will be greater than 1. The last one I'm including here is not normally thought of as trigonometry, but since it's the study of triangles, it makes sense to incorporate it. It doesn't actually use the angle at all. It uses just all three sides together. Usually we write it as a squared plus b squared equals c squared, but the opposite squared and the adjacent squared add together to give the square of the hypotenuse. We call that Pythagoras' theorem. For the non-right-angled triangles, we've got a bunch of different formulae. I wonder if you found all three. The sine area formula, this one's not a way of connecting the side lengths and the angles so much, but it's a way of calculating the area of a triangle, provided you know two sides and the size of the angle in between those two sides. We can call it half AB sine C, or equivalently half BC sine A, etc. Because as long as we have two sides and the angle in between, this formula will always work. You should notice as well that the way this triangle has been labelled, because there's nothing special about any of the angles, it needs to be something that works regardless of how we label the angles. So the angles are usually labelled with capital letters A, B and C. The side lengths opposite the angle with the capital letter is given the lowercase equivalent. So side lowercase a is opposite angle capital A. And in this context, lowercase a represents the length of a side, so it might be in centimeters or meters, and then capital A will represent the size of the angle, which for now we measure in degrees. The sine rule is a formula which involves only the sine ratio, and the cosine rule involves cos, as you would expect. But the sine rule is interesting because it looks like a three-sided equation. A over sine A is equivalent to B over sine B, which is equivalent to C over sine C. Essentially, when we use this, we pick and choose. We find a side and an opposite angle, and we divide one by the other. Or we divide a side by the sine of the opposite angle, and we find that that always gives the same result as doing it with a different side and opposite angle pair. The cosine rule, a squared equals b squared plus c squared minus 2bc cos a, is a way of connecting three sides and one angle. So if you know three sides of a triangle but you don't know any angles, cosine rule will help you to find one of the angles. If you know two sides and the angle in between, cosine rule will help you to find the third side. If you know two sides and an angle that isn't in between, then in fact you already have the requirements for sine rule, because sine rule will let you deal with a situation where you have a side and the angle opposite and one other thing. A few extra questions you might find helpful to investigate. I've labelled these two sections as right-angled triangle and any triangle, because it's important to realise that non-right-angled trigonometry is not restricted to non-right-angled triangles. If you have a triangle and you don't know whether or not it's right-angled, it doesn't matter. You can still use the general formulae. So it's worth trying what happens when we do have a right-angled triangle and yet we still apply the sine area formula or the sine rule or the cosine rule. See what kind of results you get. Pause, substitute 90 degrees in for some angles and see what happens and see what you notice. Next, we're going to work on a few questions relying on just right-angled trigonometry so that we can get a sense of where the non-right-angled trigonometry results come from. The right-angled trigonometry results essentially are the definitions of sine, cos, and tan. They're defined as the ratios of the sides of a right-angled triangle. But the other results, cosine rule, sine rule, for instance, they are less obvious. They must come from the same definitions, but it's worth working through to see where they come from. So we're going to start with this triangle, which is not necessarily right-angled, certainly doesn't look it. And we're going to use right-angled triangle first to find the height using right-angled trigonometry, and from the height we can calculate the area. So the base is 9 centimeters. There's a 4.5 centimeter side on the left, and by working out the height first, you should be able to find the area of the triangle. Give this a go. Pause the video, work through it for yourself, and when you're ready, you can compare your answers to mine. So if we have the height h, then we can use sine theta equals opposite over hypotenuse. In this case, theta, the angle, is 45 degrees. So we have sine of 45 equals the opposite side h divided by the hypotenuse, 4.5 centimeters. So I'm just focusing for this bit on this triangle here, which we know is right angled because the height literally means the perpendicular height. You drop a perpendicular from the top of the triangle. Imagine dropping something straight downwards. It falls straight downwards and lands perpendicularly falling onto the base of the triangle. The next thing we can do is use the fact that we can rearrange to get the value for h, 3.18 centimeters. And finally, the area of the triangle is equal to the half of the base times the height. And because the base is 9 and we now know the height, we can work out the area. Now what I'd like you to do is work through the problem again, but this time replace 9 with the letter A, replace 4.5 with the letter B, and instead of using 45 degrees, use a capital letter C, and see if you can generate an expression for the area in terms of little a, little b, and angle capital C. Pause, try it. When you're ready, unpause. Hopefully you found the sine area formula. It turns out that 4.5 and that 9 that got multiplied together, well, it wasn't just 9 times 4.5, it was 9 times 4.5 sine 45. That 3.18, that's where it came from. So we're using a half AB sine C. It's just that B sine C is equivalent to the height of the triangle. That's where this formula comes from. Now there's something interesting that we can do with the sine area formula. If instead of looking at the 9 centimeter side and the 4.5 centimeter side, or looking at the more general triangle down below, instead of focusing on, let's say, sides A and B with the angle in between capital C, if instead you used sides B and C and the angle in between was capital A, nothing stops us applying the same logic, working out the height, which will be different potentially. The base will be a different side, and the height will be the height from the point we've chosen. So you might need to rotate the triangle in your mind if you're thinking about this from different places. But if a half times A times B times sine of capital C gives the area, then it should also be true that if we do half of BC sine A or half of AC sine B, those should also give the area. And if they all give the area, then they're all the same. So we could say, for instance, that half AB sine C is equal to a half BC sine A. You might be able to see where this is going. See if you can rearrange this equation to generate another formula connecting little a, little c, big A, and big C. Let's see what we've got. Well, we've generated something that looks a bit like this. We've got A over sine capital A equals C over sine capital C, or B over sine capital B equivalently. Effectively, we can have any and all of those. Each one is equivalent because every single one can be generated by doing a similar thing to what we did. They're related to the fact that the area is the same and you can calculate it in 3 different ways. So that's where sine rule comes from. For this question, we're looking at the same triangle and we're still interested in the height. That's the key bit that will allow us to connect things together for this triangle. But I'd like you to see if you can work out the length of DC, which is not 9 centimeters. That's the complete length AC. But DC along the bottom, That distance, if you could work that out along with the height of the triangle, that should allow you to find the length of BC. In other words, the unknown third side of the triangle. We've got two sides, we've got the angle in between, so you might be able to guess which rule we're working our way towards. But see if you can get to it only using right-angled trigonometry. Pause the video, give it a go, see how you get on. Here's the first thing I did. I've got a right-angled triangle over there on the left. That's this one here. We can use the fact that the opposite side is h and the hypotenuse is 4.5, so we can calculate the size of h, which I get to be 3.18 centimeters. The next thing I can look at is cos of 45, which will allow me to work out the length of AD. This one, incidentally, is also 3.18 centimeters. It's a coincidence in this particular case because we've chosen 45 degrees, so we've got a particularly special right-angled triangle. It's an isosceles right-angled triangle. But I've color-coded this so you can see if we tried it with a different angle, then those two numbers will not necessarily always be the same. The next thing we can do is use the fact that we've calculated the length AD to work out what's left, the length DC. We know that the full base of the triangle is 9, so we can subtract 3.18 and we get 5.82. Now, with the 5.82 and the 3.18 from the height, we can do a bit of Pythagoras. We've got two sides that we know. We can square them, add them together, square root, and it will give us the length of the hypotenuse. And we've got BC, 6.63 centimeters. Now, if you want to try to do this one algebraically, it's somewhat more of a headache. It's quite confusing to try to put everything in the right places. So I'm going to talk you through it. But what I'd recommend is, if you think you see where it's going, then pause the video, see how much you can get on your own. And if you get in a muddle or you get a bit stuck, watch a little bit more, then maybe pause again, see if you can make sense of the next bit for yourself, see how much of it you can create before you watch me do it. So one thing that it's worth being aware of with cosine rule is that it's like a generalized version of Pythagoras' theorem. It's got all the a squared and b squared and the c squared stuff going on. It just has an extra bit, which I like to think of as an adjustment term. If you tried substituting in 90 degrees earlier, you'd have noticed that cosine rule, by adding or sometimes subtracting a bit from the b squared plus c squared, allows us to generate the third side of a triangle for different angles other than 90 degrees. So we're going to use the Pythagoras idea on this one, and we're going to make use of the fact that we can break the base, AC, into two separate pieces, AD and DC, that together will add up to give the complete length of the base. First, though, we're going to have to label things. So we'll start with side length A, which is opposite angle A, side length C, opposite angle C, and then at the top, we've chopped that in half, so I'm not going to label angle B, but the side with length little b is also been broken apart, not in half, but if we label those as well, let's call this one x because we don't know the length, and that means this bit will be b minus x. So I want to make use of the fact that we know that base will be little b, but I don't want x to appear in my final formula because I don't want to have to know what x is. I just want a link between little a, little b, little c, and angle A, let's say. Also, we're going to need the height of the triangle. That's part of how we're going to build this up because we're going to make use of the fact that we've got two right-angled triangles in our picture. So let's begin with triangle BAD, the one on the left. We can start out with Pythagoras. We've got x, h, and c. X and h are the two legs of the right-angled triangle. C is the hypotenuse. So c squared is given by h squared plus x squared. We've also got triangle BCD, the one on the right-hand side. And we've got a hypotenuse of A, and then the legs are h and b minus x. So we can sub those in as well. Now, try to focus on what we're trying to get rid of. When you've got lots and lots of letters going on, it can get a bit bewildering. But the aim, when we're trying to develop a formula, is to get rid of the letters that we don't want to appear in our final result. But we're happy to hang on to the letters that we don't mind about. So I don't mind about A or B or C, but I want to somehow find a way of eliminating h and eliminating x. Well, the easiest one to start with here is going to be h. We can see that h squared appears in both of those equations. And since both equations must be simultaneously true, I can make use of that fact. I can either rearrange and substitute, or something else nifty. I'm going to eliminate h by saying that h squared is simultaneously equal to c squared minus x squared, but also equal to a squared minus b minus x all squared. So those two things must be equal. We can do a bit of simplifying and expanding. So we can square the b minus x bracket, and then we need to take it away from a squared, and that will be equal to c squared minus x squared. Some things are going to cancel straight away. If you look carefully at that bracket on the right, we're taking away b squared, we're adding 2bx, and we're subtracting x squared. Well, we've got a minus x squared here, and we've got a minus x squared in here, so some things are going to cancel straight away. And immediately this starts to look a bit more like the formula we want. You might need to move a few terms around onto different sides, but we can make it look like this. A squared equals b squared plus c squared minus 2bx. It's very nearly what we want. The only thing we need to deal with now is x. And if you think about it, there's something else that we've not got that we were expecting. If we have a squared equals b squared plus c squared minus something, the something should be 2bc cos a. So I just need to convince myself that little x is equal to little c times cosine of capital A. And we can get that directly from triangle BAD by using some right-angled trigonometry. We can see that cos of A is going to be the adjacent side x divided by the hypotenuse c. So now we can replace x. Sub that in, and now you're staring at the cosine rule. The next thing I want to do is investigate an interesting phenomenon. I'd like you to use the sine area formula to calculate the area for each of these triangles. They both have the same base, 8 centimeters, and they both have a 6 centimeter side, but the angles between the 6 and the 8 centimeter sides are quite different. One is much bigger than the other one. So have a go at calculating the areas and see what you notice. Perhaps before you work them out, eyeball the shapes and decide which one you think is the biggest, and then see if you're right. Well, if you've done this correctly, you should have 12 centimeters squared for both of these triangles, which might be a little surprising to you. You might be thinking one of them looks bigger than the other one, but in fact, it is possible to chop them up and rearrange them in such a way that they are basically the same. They cover exactly the same amount of space. And that may be a little hard to fathom, but one thing we can use here is the height of the triangles. If you look carefully, you can use a bit of right-angled trigonometry, just like we were doing before, to perhaps split the triangle on the left by drawing a line down here. Use our right-angled triangle rules. If we do 6 times sine 30, that will give us the height, which is 3 centimeters. And in fact, that right-angled triangle that's in this shape is exactly the same right-angled triangle that is missing from this shape. 150 leaves an angle of 30 degrees just there. So those two triangles are the same triangle, and therefore the height must be the same. And if the height of the two triangles is the same and the base is the same, then the area must be the same. You can drag that top point as far as you like horizontally, and even though it will give you quite a wide triangle, the wider it gets, the narrower it will get. So it will never take up a greater or a lesser area. If the base is the same and the height is the same, the area will be the same. In general, this gives us a rule that's worth hanging on to. It's not something special about the 30 degrees that makes this work. It's the fact that 30 degrees and 150 degrees complement one another. One completes the other one. What do they make when you put them together? Well, a straight line, a perfect half turn. 150 goes with the 30 degrees, as you can see here on this line. So those two angles are complementary angles. And we can see that in the formula, when we did half of 6 times 8 times sine 30, and then half of 6 times 8 times sine 150, we got exactly the same answers. That's because sine 30 is a half, and so is sine 150. And in general, we can make use of this result. It's an example of symmetry within a function. Different inputs giving the same output. And in this case, you can always get the same result for sine, whether you use a particular angle or its complement. So sine of 1 degree and sine of 179 degrees will both be the same. Sine of 84 and sine of 96 are both the same. Sine of 45 and sine of 135 are both about 0.71. you're always going to get the same result if your two angles add up to 180. In other words, if they average out to give a right angle. That's another way of looking at it. You might be interested in cosine. Cosine does have symmetry, but of a slightly different sort. In fact, you can try this out. You might want to try what happens when you do cosine of two complementary angles like this. Cos 30 and cos 150 are not the same, but they are related, and you might want to think about what that means and how it's represented in the diagrams above, perhaps. You could even try using cosine rule to work out the length of the third side. That's clearly different for each of these. We're not going to get exactly the same answer when we work out the length of this side and the length of this one here. They're going to be different depending on the size of that angle, the 30 degrees or the 150. And I'd encourage you to try one more thing, which is, what if that angle isn't 30 or 150? What if it's 90? What if you're looking at a right angle triangle with shortest sides 6 centimeters and 8 centimeters? Compare that answer to the two answers you get for these two triangles and see what you notice. Maybe drill down into your cosine rule formula and see why it works the way it does. The next thing to look at is something called the ambiguous case. Sometimes you're given some information about a triangle, but not enough to know exactly what the triangle is. The obvious example would be, I'm thinking of a triangle with a side length of 10 centimeters. If I don't tell you anything else, there's all sorts of triangles it could be. Not just any odd triangle, but there's lots of different kinds. There's whole infinite families of different possibilities. If I give you a bit more information, maybe it narrows it down. If I make a triangle with side lengths of 3 centimeters, 4 centimeters, and 5 centimeters, it is going to be identical to any other triangle that you make with lines 3 centimeters, 4 centimeters, and 5 centimeters. In fact, we could get 3 sticks of 3, 4, and 5 centimeters in length, join them at the ends, and our triangles would perfectly match one another. Not only that, but we'd be able to use that to generate a right angle. That's what the Egyptians did. They reckon when they were building the pyramids, they'd use knotted rope, 3 knots, and then 4 knots, and then 5 knots. And if you held them at the right places and pulled them out into a triangle shape, then you'd be basically holding the world's largest set square, and you could use it to map out right angles on large pieces of construction equipment, like pyramids. Now, this is the sneakiest example of an ambiguous case where it looks like you're given enough information to describe your triangle, but you're not quite. And it's not that there's an infinite number of possible triangles. It's more like there's just not quite one triangle. There are in fact 2 triangles that have 2 adjacent sides of 4 centimeters and 2.5 centimeters, and also an angle of 30 degrees that's touching the 4 centimeter side but not the 2.5 centimeter side. Those facts are true for both of these shown in the diagram, and yet the 2 triangles are very different to each other. One is obviously a lot bigger than the other one, but they both have the same description. We've got an angle, and then a side length, and another side length. They're not congruent to each other. Congruency conditions include all 3 sides the same, or 2 sides and the angle in between, or perhaps you know it's a right angle triangle and you know the hypotenuse and one other side. Things like that will allow you to narrow down exactly which triangle you're dealing with. This one, we don't have congruency. We don't know that the 2 triangles are the same. So what happens when we try applying one of our rules? Well, the sine rule should apply, so we get this result. If we're trying to work out the angle, one of the other 2 angles, and perhaps we want the angle that's opposite the 4 centimeter side, that would make sense. So we're trying to work out what this angle would be here. We'll call it theta. But of course, in this triangle, as far as the formula is concerned, it's the same. 4 over sine theta is going to be the same as 2.5 over sine 30. And it gives us the same result for both, 4 times sine 30 over 2.5. So what's going on? Well, we get sine theta equals 0.8, and the calculator will duly tell you that theta is about 53 degrees, which seems to fit with the second triangle, but it doesn't seem to fit with the first one. There is obviously another angle, and in fact this comes right back to what we were talking about. The complement of the angle will have the same sine. So if we do sine of 53 degrees, we know that 180 minus 53, or 127 degrees, will give the same result. Sine of 127 is the same as sine of 53. Those 2 angles add to make 180, so they have the same sine. What I'd like you to do now is make use of the results on the screen, so I'll leave them up here for a moment, and have a go at a few fluency questions. I've picked out some questions from the first 4 exercises. Question 3 from the first exercise in the chapter, question 9 from 9b, question 2 from 9c, and question 2 from 9d. There's a mixture of things in there on cosine rule, sine rule, the sine area formula, and some of the ambiguous case questions. When you've tried those, we're going to look at some meaty triangle problems that can get rather complicated, and you're using these results, but you're using them in a somewhat more sophisticated way than what you might be used to from even higher GCSE. Now let's try a more sophisticated problem. We have a triangle where we're told the perimeter, one of the sides, and one of the angles, and we're asked to calculate a bunch of things. Now, with this particular triangle, we're given the perimeter and one of the side lengths, so certain things are fixed, and you might start by visualizing something like this. The base is 7 centimeters. The other 2 sides are constrained by the fact that the total perimeter needs to be 15 centimeters. So we know that as one of those sides gets longer, the other side has to get shorter, and there's a limited range of possible triangles we could be dealing with. The other thing to be aware of whenever you're dealing with a complicated problem like this, in addition to trying to draw a diagram, is to think through a general problem-solving schema or process. I think of this as input, process, and output. So the input would be asking ourselves, what do we know? What information has the question provided us with? And for starters, they've told us the perimeter of the triangle. They've also given us one of the side lengths, and they've told us one of the angles. Now, what is useful, generally speaking, and broadly speaking, when you're dealing with any sort of problem, there may well be irrelevant information, there might be missing information, there might be erroneous information. In the case of a maths problem that you're going to find in an exam, typically every single bit of information is useful. It's been chosen specifically because if they didn't tell you it, you wouldn't be able to solve the problem. And if they have a piece of information in there that you don't need, then it's not really worth having. So they typically won't have that. You're not going to have unnecessary information provided. So if you find yourself stuck in the middle of a problem and then you look up and you realize there's a bit of information you've not used yet, it tells you that theta is obtuse or something, and you think, I've not made use of that, why not? That might be the bit that's causing you trouble. You can't get any further because there is a necessary clue. Every clue included in here is required. That's a good way to think of these problems. Now, the process you follow, this is where you start thinking about the possible routes you could take from what you know. What kind of things could you work out? And some broad clues. If we're dealing with triangles, chances are you're going to need some trigonometry results. It may well be that there are some key words that you look out for that give you a clue that you're dealing with a particular topic. So bear that in mind when you're thinking about what kind of things you might do. But don't dive into a problem until you've clarified exactly what it is you're trying to get to. Even if you don't know how you're going to get there yet, try to make sure you know where you're heading. In this case, they've asked me for the lengths of AC and BC and the area of the whole triangle. So that's where I'm trying to get to. You might want to ask yourself, well, what would I need in order to get there? And if you can work out what's necessary to get the final results, and you can work out what you can do with what you've already got, very often it becomes easier to make the link in the middle, so you've got a coherent chain from the information you have all the way to the result that you need. Now, given the information we've got, we can start annotating our diagram. We can get something hopefully that looks reasonably accurate, so we can use it to verify our results at the end. So let's use this. We've got a base, which we're going to label up in the same way they've labeled it in their question, B, A, and C. You'll notice when they have an angle, if they describe it as angle BAC, it literally means the angle you go past when you walk from B to A and then from A to C. They do that because sometimes there's more than one angle at a particular point on a diagram. In this case, it's fairly obvious which angle we're dealing with. Now, the other thing I've done is I've labeled the two sides, x and 8 minus x. The reason for this is that I don't want to clutter up my diagram with unnecessary variables. I don't know either of those two side lengths, but I do know that together they add up to 8 because I'm told that the perimeter is 15 centimeters. And a good check here to see if you've made yourself a decent diagram is to go back through the question and see if every bit of information you were given is somehow represented on the diagram. This is just as true for geometry problems as it is for a mechanics problem. There might be a long, wordy paragraph that's very dense, very high information density. There's a lot of information on every single section. But if you can pull it out and synthesize it and put it in a diagram, then you can see it all together and your brain can start making connections. So we've made full use of the perimeter statement. We've encoded that information into the fact that we have x and 8 minus x on those two sides. We've used the fact that AB is 7, that's marked on the diagram, and angle BAC is 60. So now we can kind of focus our efforts on looking at the diagram. Think about what we can see. We've got one angle, we've got 3 sides. Now we could label other things. If we thought that finding another angle might be useful, then we could label up the angle at B or the angle at C, and then perhaps sine rule would come into play. But if we did that, we'd have 2 unknowns involved in our equation. Yeah, we've got x over sine 60 perhaps, but that's going to be equal to 7 over sine C, and we don't know what angle C is. So that would probably cause us more problems than it's worth. 3 sides and an angle sounds like cosine rule. So if we can substitute our 4 numbers into cosine rule, we should get an equation that only involves one variable, x. So that's what I've done. We have x squared equals 7 squared at 8 minus x squared minus 2 lots of 7 times 8 minus x times cos 60. That's a squared equals b squared plus c squared minus 2bc cos a. And if in doubt, write out the complete formula first before you substitute things in. This is the 3rd time I've recorded this slide because I've kept making mistakes as I went through, and I only find them when I start talking through what I've done and thinking about the steps I've followed. So it's easy to mess up even if you've done it 100 times before. Be on the lookout for the little slips that can creep in. Now I can simplify this. There's a few things we can do. For a start, although it might look complicated, it is actually just a quadratic equation involving x. It's got some x's, some x squareds. The cos 60 shouldn't bother us because although it's got a trig function in there, it's a trig function of a known angle. So cos of 60 is exactly a half, it turns out. So cos 60 is going to cancel quite nicely with the 2 over there. And we can turn that bracket into 7 times 8 and 7 times negative x. The 8 minus x bracket, that can also be expanded out so that we can start simplifying things. So let's do a bit of that. 8 minus x becomes 64 minus 16x plus x squared when we square it. And then we have the minus 56 and the plus 7x from the other bracket. We can group things a bit and simplify. And you might notice at this point as well that x squared appears on both sides. So we can subtract x squared from both sides of the equation. And this, what seemed to be a quadratic equation, has degenerated into a linear equation. And we can solve it and find x. At this point, don't forget we created the variable x, so x equals 19 over 3 doesn't tell the examiner anything that they want to know yet. We've been asked for the lengths of AC and BC. And this is going to be helpful because when we look back at what the question has asked us for, we can check to make sure we've answered exactly what they've asked. We might feel like we've done a good job, we've done the hard work, but we've not interpreted our result yet. So we need to notice that BC, which is what we labeled as x, is 19 over 3, and that we can calculate AC, that's 5 over 3. And if you don't write that down, you'll make the mistake that I made a minute ago, where I used 19 over 3 in my next equation instead of 5 over 3. Because the last bit will be the final thing they've asked us for, which was the area of the triangle. And remember, our area formula uses 2 adjacent sides and the angle in between. We've got 7, we've got 8 minus x, which we actually now know is 5 over 3, and we've got the 60 degrees. So we plug it in, half AB sine C, and sine of 60, it's not quite such a nice number, it's actually root 3 over 2. And you can get an exact value for the area of the triangle, which is a good idea. You should write 35 root 3 over 6, but it's also a good idea to include the approximate value 10.1 centimeters squared. If nothing else, for your own peace of mind, to check that your answer is correct. The first time I worked through this problem, I got an answer of about 3 centimeters squared. And just looking at the diagram, with the numbers I've got should have told me that that was a bit off. We can estimate the area of this triangle if we've got a reasonably accurate diagram, because I already know that the side lengths, roughly speaking, we've got about 6 up here, got about 2 down here. So our triangle is probably, when it's not exactly a height 2, but height 2 will be a reasonable approximation for it. So if we think about a triangle of height 2 and base 7, the area is going to be approximately a half of 7 times 2, or 7-ish. We've got 10. My estimation was 7. They're pretty close. I'm happy with that. Here's another problem. ABCD is a square. Angle CED is obtuse. Find the area of the shaded triangle. This is another classic example where we have to do quite a bit of work to find our way from the information given to the information that we're asked for. I'd encourage you to stop and work through this once I've talked through the general pattern. Remember, we start with the input. Think about the information that you've been given already. Some of that is on the diagram and some of that is given in the text. And then what can we do? What kind of results do we have? What are we able to use? What's in our mathematical toolkit for this type of problem? And then finally, what do we need? How can we verify it? I'd encourage you now to pause the video and think about your game plan. Think about the plan of action, what you might work out first, and then what you might work out next, and how that's going to help you to get eventually to the area of the shaded triangle. You may well consider and reject a few different plans before you come up with a plan that you think is workable. You know that it works, you know why it works, and you know that it's reasonably efficient compared to the other plans on the table. So see if you can come up with your plan first before you start executing it. So here's my plan. I've decided that based on what I can see on the diagram, it should be fairly easy to work out the angles in triangle CDE. I can see we've got a 40-degree angle. That's angle EDB, and D, or the angle CDB, is a right angle because it tells us ABCD is a square. So I can work out one of the angles in that triangle already. I already know 2 of the side lengths. Because ABCD is a square, there's extra numbers I can put on this diagram straight away and fill in some bonus information. Once I've got that, I've then got all sorts of tools at my disposal for working out other things within that triangle. And the purpose behind this is to see if I can find the height of that triangle. Once I've got the height of CDE, I could use it to work out the height of the triangle I actually care about. Because remember, they're both inside a square. So if I know how tall triangle CDE is, and I know how tall triangle ABE is, because those two add together to make 10. Once I've got that, I can just work out the area of AEB, because I will know its height. So that's my plan. And I'm going to work through it bit by bit. But on this one, it's not going to look quite so linear. It's going to be dotted around the diagram because that's where I'm going to do the working out. Some questions just lend themselves better to this process. So I'll start by looking at this angle, and because angle CDB is 90 degrees, I can fill in that 50 degrees there. Another reason why having a big diagram is helpful. There's going to be a lot of annotation, and the bigger it is, the clearer it will be for both you and the examiner. The next thing I notice is that, well, ABCD is a square, so let's fill in the 10 centimeter line. And now I've got that, it becomes clear that I've got enough going on that I can start calculating other angles or sides. I've got the 8 centimeter side, which is opposite the 50-degree angle. I've got the 10 centimeter side, which is opposite an unknown angle. So, bit of sine rule, and I can find the value of that unknown angle. But then this is the bit where I nearly tripped up. So I've got to be very careful. When I look back at the what do we know section, not everything that we know is on the diagram. ABCD is a square. Yeah, I can incorporate that. I notice the right angle. I notice the 10 centimeter side on CD. And I'm going to later use the fact that AB is also 10 centimeters, but angle CED is obtuse. Classic example here. What's the relevance of that? Well, that's where the ambiguous case comes in. If you know that sine theta is equal to 10 over 8 times sine 50, that's all well and good, but if you then do inverse sine and assume that you found the correct answer, you might well be wrong. The correct answer is 106.8. So if you've got an answer of 73.2, it's not the right answer. From the diagram, it's not particularly obvious. That angle on the diagram is deliberately ambiguous. They've drawn it so it kind of looks like a right angle, so you can't really tell, but they've told you in the description that that angle is obtuse. So if you've got an acute angle, it's definitely wrong. At least if you notice that yours is acute and theirs is obtuse, that should flag up in your brain that we're thinking along the lines of how could there be another angle that works. So the complement is the angle you're looking for. If your angle isn't the angle we need, then try 180 minus that angle, because that will also satisfy sine theta equals 10 over 8 sine 50 or whatever you happen to have. The next thing I do is this. I've got two angles in a triangle. It's easy to use the fact that angles in a triangle add up to 180, and that gives me this angle over here, 23.2 degrees. And now, think about my game plan. I found all the angles. Now I want to try to find the height. And I can do that now. I've got the side length 8 centimeters, and that's adjacent to the angle of 23.2 degrees. In fact, it's the hypotenuse of a right-angled triangle where the opposite side is the height that I want. So I'm going to use sine 232 equals the opposite, which is h, height, if you like, divided by the hypotenuse of that little right-angled triangle, 8 centimeters. So the triangle I'm visualizing here is this little one here. And h will be that height. So now I have the height, 3 point something centimeters, and the next bit, these dominoes start falling down really quickly now. I know the height, so I can work out the height of the other triangle. This will be this distance here. And clearly, the two must add up to make 10 because we're looking at a square. So I've got that height as well. The last thing to notice is that, of course, AB is also 10 centimeters. So I can work out the area of the triangle I was asked for by using half times the base of 10 times the height of 6.84. I've got a shaded area of 34.2 centimeters. We can do a quick check as well. Like I said, my diagram's not perfect. It's deliberately not drawn accurately, but we can get a rough idea of whether our final answer is sensible, because we're looking at a slice taken from a 10 by 10 square. A 10 by 10 square has an area of 100, and we're looking at a slice that purports to be approximately a third of that. And it looks like about a third, so I'm happy with that answer. Now there are a bunch of tricky questions for you to try. So we've got a couple of questions from 9A, questions 14 and 17. We've got question 12 from 9B, question 6 from 9C, and question 14 from exercise 9E. Try each of those, make use of this input processing output method, and see how you get on. This next problem is quite a challenging one. Not only are we dealing with a shape that doesn't obviously look like it has anything to do with triangles or trigonometry, but we have a situation that's going to involve the ambiguous case. We're given the area of a particular triangle within the shape, ABC, and we're asked what could the area of the entire quadrilateral ABCD be. Now, anyone who's ever tried to build a rectangle or a square out of pieces of wood or something will realize that unlike making a triangle, just having the four lengths that you want to use is not enough to uniquely describe the shape. If you imagine building this shape, for instance, out of 3 or 4 or 5 and a 6 centimeter piece of wood, then connecting them at the corners, unless your connections at the corners force the angles to be something specific, then what you're going to find is there's a bit of flex and wiggle in this. This is the reason we have such things as triangulation. When you build something, if you look at particularly any big structure like a bridge that's supposed to bear heavy loads, it's going to have triangles all the way through, because a triangle, just by nature of having only 3 sides, forces all the angles to remain the same. Whereas if you try building something a square shape, for instance, and give it a little nudge, suddenly you've got a rhombus. So imagine this shape moving and flexing. We've got a variety of different possible shapes that it could end up being. We are told the area of the triangle, so that should limit things a little bit and restrict the situation, but not necessarily completely. So I would anticipate there'd be 2 possible answers. The first thing to do with this question would be to recognize what information we've been given. So we're told about the area of the triangle, which means I'm going to draw on the line to make the triangle ABC. And then in order to make sense of the area of this shape and to think about how I can use that area information, Well, think about the formulae we have for the area of a triangle. The basic one, half base times height, is not so useful here because we don't know what the height of the triangle is. But half AB sine C, that could be relevant. We've got two sides, so if we also include this angle theta in the bottom corner, we can describe the area as half times 3 times 4 times sine theta. Another thing that might be useful is this length x, because in order to work out the total area of the whole quadrilateral, we'd need not just the area of the triangle ABC, but we'd need to add on the area of triangle ACD. And if we only have two sides, that's not enough. Whereas if we can calculate the length of that third side, suddenly we'd have enough information to calculate the area of that triangle. It's still not particularly trivial to find the area of a triangle from three sides. There is a fancy formula called Heron's formula that you can look into that does precisely that. It needs only the three side lengths in order to calculate the area. But that's not something that's on the A-level maths syllabus, and it's not something you should be expected to know or reproduce for yourself. What you can do when you've got three sides to a triangle is use something like cosine rule to calculate an angle. So for instance, we could find this angle in the top corner. And once you've got that, I suppose you'd be able to use the same formula for area, half AB sine C, that we were talking about before, and calculate the area of that final section ACD. So let's think about this in terms of a problem-solving process. We have the input, we have the processing, and we have the output. Ask yourself some of these questions. What do we know, and what's useful? What can we do? What might help? What do we need, and how can we verify things? So think in terms of the starting point. I've already annotated my diagram a little bit, which is, in fairness, part of the processing, but also part of the input. So I'm thinking about the best way to represent for myself what I know about the situation and what might be useful to work out along the way. And then thinking in terms of the different rules and formulae that we have, consider where we're trying to aim and what sort of result we're looking for. And then maybe ask how we can verify the answers at the end. Is there anything we could do to do a quick sense check, for instance? So I might glance at that and say, well, okay, if I'm making a quadrilateral with side lengths of 3, 4, 5, and 6, I don't suppose the area is going to be massively different to the area of a square with side length 4 or 5. So maybe I'm expecting answers like 16 or 25 square centimeters, something like that. In this particular case, notice I've not given any units. So by default, you might have to give your answers as square units rather than square centimeters. But for now, we're not going to worry about that distinction. Let's think about a game plan. What sort of things should we be doing? This is our bullet point plan that is very often a really, really useful part of dealing with any big, complicated problem that's not been broken down into steps for you. So I'll work through the steps one by one. This is what I aim to do. And then if I can complete those steps, hopefully I'll have a route through to the solution. I can find theta for a start. I should be able to do that by thinking about my half AB sine C formula, using the fact that I've been told the area of that triangle. Once I've done that, I could find x. Now, by that point, I will have two sides and the angle in between, which means I should be able to use the cosine rule to calculate the length of the opposite side. And then I can find alpha. At this point, I'd be looking at the other triangle, the ACD triangle, and I'd have three known sides, and I'd be looking for an unknown angle. So again, cosine rule, but with a different triangle. And then find the area of triangle ADC. Finally, put it together and get the total area. So if you want to pause and give this a try, now you've got a game plan and you've got some variables to work with, I'd encourage you to try it. Remember, at each stage, you're going to find probably two different valid solutions, because there isn't just a single angle that will allow me to get a triangle with that area. If you imagine making the angle very, very small, you can have a tiny area. But equally, if you make the angle close to 180, you'll also have a tiny area. And the maximum area will be somewhere in between the two. Once you've got your two possible angles for theta, you'll get two possible angles for x, two possible angles for alpha, and two possible values for the area of triangle ADC. So give it a try. When you're ready, unpause, and I'll show you my working out. So here's what I get for theta. Half AB sine C gives me sine theta equals √3/2. This gives a couple of nice answers. Notice that the first answer, 60 degrees, comes directly from the calculator. That's just inverse sine of √3/2. The second answer comes from using the symmetry of the sine function. The fact that if we subtract the angle from 180, we get another angle that works just as well. Sine of 120 will give me the same answer as sine of 60. Essentially, those two angles are mirror images of one another about the line theta equals 90. So 90 degrees is the sweet spot in the middle. And in fact, it turns out if you want the maximum area, you would want the angle between the 3 and the 4 to be 90 degrees. If you go beyond 90, the triangle starts getting smaller again. If you go before 90, it starts getting smaller. It's obviously of size 0 if theta is 0 or 180, but it's of maximum area, which would actually be 3 times 4 over 2, or 6, when theta is equal to 90 degrees. So now we've got our two values of theta, we move on to the next step, finding x. This is going to involve cos theta. So I first work out the two possible values of cos theta using the fact that I know that theta is either 60 or 120. And if I try using cosine rule and then substitute in either a half or minus a half, I get two different values for x squared. That gives me x as either root 13 or root 37. You'll notice I'm only including the positive square roots because these represent lengths, so I can already rule out negative values. The next step is finding alpha. For this, we're going to need cosine rule once again. But this time, because we know the value of x, or the two possible values of x, I can substitute those in, do a bit of rearranging, and find, once again, two possible values for cosine alpha. Once I've got those two values, I can find two values for alpha, 36.9 or 67.5. And the next step will be finding the area of ADC. Half AB sine C will do this for me. And remember, because I've got two possible values for alpha, I'll have two possible answers for the area. And one of them is a bit smaller than the other one. And that will give me two different numbers that I can calculate for the total area of the entire quadrilateral ABCD. Just briefly, to illustrate the flexibility we've got here, so a quick animation to show if we start messing with the angle at ABC, the angle that we called theta before, we can find a range of different possible quadrilaterals. The two sweet spots are indicated with the green lines, they're green circles. So for instance, on the left, we've got this one. The area of the triangle at that point is correct, 3 root 3, but that gives us the 60 degrees in the bottom right corner, gives us a root 13 for the dotted line, and it gives us 36.9 degrees for the top corner. On the right hand side, we get this version, where the angle is bigger at the bottom, the length of the diagonal is larger, the angle at the top is larger, and the overall area is larger. If you're wondering how, in general, to find the maximum possible area for a quadrilateral, it actually turns out to be a little more complicated still than this, but the idea would be the same. We're looking for what happens as you mess with one angle, what's the effect on the diagonal, what's the effect of that on the other angle, and roughly speaking, if you're looking for the largest possible four-sided shape, it's going to be the one that most closely resembles a circle. So that's kind of the aim of where you're going with an optimization problem like that. But that's a little bit beyond the scope of what we're doing here. Now for the bonus section. So if you're still with us, well done. This might be a section to come back to at a later date. If you've done this video for the very first time, take on board what we've been doing with triangle problems. But if you're still curious and you want to see a little bit more about what's coming up next, trig graphs is where we're going with the next section. Here is a diagram. We have a point moving around a circle. I'd like you to write down anything you notice about the point and anything you wonder. Things have been color-coded to help you a little bit. If the point is moving at a nice regular pace around the circle, you can see the rate at which the two numbers change. You can see the sign of the numbers, as in positive or negative. A couple of useful questions to ask. What stays the same as the angle changes? What changes as the angle changes, and how? Hopefully what you've noticed here is that this point has coordinates cos theta, sine theta. Cos theta essentially tells you how far to the right of the origin you are. So it starts out at 1, because if the angle's 0, then you are as far to the right as you can be. But then as the angle increases up towards 90, cos theta shrinks to 0. And as the angle, as it is now, gets closer to 180, cos theta is giving an answer closer and closer to -1. And then after it gets to -1, the angle becomes a reflex angle. It's going to start coming back up towards 0 again. Meanwhile, sine starts at 0 and increases all the way up to 1 by the time we get to sine of 90, and then goes back down again. And you can see perhaps at places like 120 where the height is the same as at 60 degrees. This is why sine has symmetry about the 90-degree mark. Essentially, it means that sine of an angle and sine of 180 minus the angle are going to be the same. Cos, on the other hand, because it's showing you the x-coordinate, you'll find that cos of, say, 20 degrees is equivalent to cos of 340 degrees. 20 degrees anti-clockwise from the x-axis is equivalent to 20 degrees clockwise. You can even think of the angle 340 as being the angle -20, if you like. Here's a slightly different diagram. This one's somewhat wackier, but hopefully it'll help you to understand why the tangent function is called the tangent function. Because the key thing about that triangle, the thing that was staying the same before, was the length of the hypotenuse. That black line is always the same. That's why you've got a little dotted line there showing you the circle. That point is constrained to that circle. It's always going to lie on the unit circle because the hypotenuse is always 1. That gives some fascinating connections between cos theta and sine theta if you use Pythagoras, and we'll get to that in due course as well. But in order to get something on this diagram that corresponds to tan, well, we can't have the hypotenuse being our denominator, like with sine and cos, where you've got adjacent over hypotenuse, opposite over hypotenuse, and if the hypotenuse is 1, then cos theta is the adjacent and sine theta is the opposite. Well, for tan, it's opposite over adjacent. We need the adjacent side to be 1. So we've made a different right-angled triangle where the adjacent side is the line linking our point to the origin, and that means the opposite side will be the tangent to the circle. It's called a tangent because it is literally a tangent. So you can think of the length of that line as being the size of tan of the angle. The steeper the line gets, the steeper the black line gets, the longer the orange line becomes. It's not quite as clear-cut when it's positive and when it's negative, because at the moment tan theta is positive. When we get to the fourth quadrant now, tan theta is negative, and when we're back at the first quadrant, tan theta will be positive again. So it does some weird things in terms of the sign of tan theta, but in terms of the length, you can kind of see what's happening, and maybe you can make sense of what's going on as we get close to 90 degrees or close to 270 degrees. One last section now. I particularly like this animation that I managed to make. We're thinking about that same point going around a circle. If we focus just on its vertical displacement, you can see as it traces it along how high it gets, how low it gets, and the rate at which things happen. This particular curve that's being traced out is showing you precisely the height of that point as it moves around in a circle. So it goes up, it comes back down, and if you focus only on the vertical displacement, you can see it moving up slower and slower, down faster and faster, and then slower and slower, and then up again. It's going around a circle at a constant rate, about 7.5 revs per minute, but the rate at which it moves up and down is always changing. If it wasn't, it would continue to move up at a constant rate or continue to move down at a constant rate, but it's not. It's going up and down and up and down. It's bouncing, basically. If you think about it just in the vertical direction, it's like a spring bouncing up and down almost. You can think about when it's moving up as fast as it ever will, or when it's moving down as fast as it ever will, or at which moments it's neither moving up nor moving down. You might also think about the sideways motion, because this whole thing is symmetrical. You could turn your head 90 degrees to one side or the other, and you'd be watching the same thing from a different direction. Can we describe that with a similar sort of curve, perhaps? And then the last thing, I mentioned bouncing on a spring, and Minute Physics have done a great video about this. You might have to look it up. I'll share the link with you if I find it. But Galileo, back in the 1600s, was convinced, as he observed the motion of Jupiter's moons, that they were attached to Jupiter by giant springs, which may sound completely daft to us, but it's because of the perspective that he had when he was watching their orbit around Jupiter. Let's see if we can make sense of that. Here is something moving in a circle. What we're going to do is rotate this so the top of that circle moves back away from you and the front is moved, the bottom of it is moved up forwards. So the ball's moving towards you and now it's moving away from you. Now it's moving towards you again, across to the right and then back and away from you. So you're watching it go around in a circle, but you're watching it from the side. This is what happens when you look at circular motion from a different perspective. If we're looking at it from above, if Galileo had been watching the moons of Jupiter from above, then it would look like a circle. But because his frame of reference was different, as he plotted the points and he looked at the motion, we glance at that thing, and if we didn't know we were looking at a circle end on, we'd be convinced we were watching something bouncing on a spring. It's constantly being pulled back towards the middle. I think it's fascinating how changing your perspective on something like this can make two seemingly different phenomena end up being the same thing. Sine and cosine are used to model pretty much any periodic function. Anything that repeats itself at regular intervals can be modeled with sine and cosine. Circular motion works perfectly for this, but it doesn't have to be circular motion. A mass bouncing on a spring or somebody dropping with a bungee rope, anything like this where you've got some kind of back and forth oscillatory motion, sine and cos will end up being useful for modeling that. If we can describe those mathematically, we can describe all sorts of things.